Hello everyone, my name is Souza and I'm going to present the paper called Effective Channel Downlink Pilot Estimation in User-Centric Self-Free Massive MIMO Networks that will appear in the Global Commun 2022 conference. This is the outline of the presentation, where I will introduce the proposed IP selection refinement and downlink pilot assignment, the numerical results, and the conclusions. Self-free massive MIMO networks consists of a large number of access points distributed in the covered area. The systems can provide a better macro diversity and less shadowing and blocking, and a more uniform user performance. However, when all access points cooperate to serve all users in the networks, there can be an immense front-haul signaling and high computational complexity in a system that is called canonical self-free massive MIMO. And therefore, it is not scalable in relationship to the numbers of users. And a solution is to use the user-centric clusters. In user-centric self-free massive MIMO networks, each user equipment is served by a subset of the access points, and the computational complexity to perform channel estimation, data reception and transmission, and the front-haul signaling does not scale with the numbers of users, and therefore it is a scalable implementation of the self-free massive MIMO systems. The new challenge is now how to choose the subset of the access point that will serve each user, and how to control the cluster size to reduce the computational complexity and disparities among the users. In this paper, it is proposed a AP selection refinement method that controls the maximum numbers of access points serving each user by using a parameter alpha. It works by initially computing a scalable AP selection approach where each access point will choose tau UP users to serve. After that, the CPU will compute the numbers of access points serving each user. And if these numbers is higher than the threshold computed by using the parameter alpha, the CPU will drop the connection with the access point that contribute the less to the user performance. And then in the end of this step, the computational complexity will be reduced. Another issue with self-free massive MIMO networks is related to the channel hardening degree. In cellular systems, the channel hardening phenomenon, in cellular massive MIMO networks, the channel hardening phenomenon occurs in where the effective channels of the users behaves almost deterministically. That is, it doesn't vary a lot. However, in self-free systems, the access points are located in different positions. The channel hardening is less pronounced, and the channel hardening is basically computed as the inner product between the channel vector and the precoding vector of all the access points serving that users. It is basically a single scaling value, and the users need to know this value in order to decode the downlink data. And due to the low degree of channel hardening in self-free systems, it may be required to perform a more reliable estimation method. In this paper, we assume that the user will estimate the effective channel by performing downlink pilot-based estimation. In this approach, the CPU will first estimate the uplink channel vector, and then we will use that to beamform the downlink pilot to each user. The user will be able to estimate the effective channel by using these received downlink pilots. And however, the numbers of pilots and samples used to the pilot transmission may not be a function of the numbers of users, since we want to achieve a scalable approach, and the numbers of users may be too high, and the numbers of samples in the coherence interval may not allow for that many pilots. So one solution is to reuse the pilot among the users, and the downlink pilot assignment has to decide which of these users will reuse the same pilot sequence. And to perform the downlink pilot estimation, after the user receives the combination of all the downlink pilot signals sent by the access points, it has to correlate its received signal with its assigned downlink pilot. And we can see in the first term that we have the channel vector of the user, the effective channel of the users, and also the interference called by just the user that will reuse the same pilot, and plus a noise. And we assume that the user will perform linear minimum mean square estimation, and that is given by this equation. And it is proposed that the users, the downlink pilot assignment will be performed in such a way that tries to minimize that pilot contamination, that interference of the users that use the same pilot. And to do that, the first tau DP users will be assigned to a orthogonal pilot sequence, and the remaining users will first compute the level of the interference in each pilot, and we'll choose the pilot that has the lowest value of interference. And this step is repeated until all users receive that pilot. And here are some parameters for the simulations. We assume that we have 100 access points, each equipped with 4 antennas serving 20 users. And we have tau UP, the numbers of pilot sequences for the uplink and downlink is equal to 10. That is less than the numbers of users, then they will be reused. And here are some other parameters. In the first result, we compare the performance of the downlink pilot assignment with the other strategies. The random pilot assignment has the worst performance as expected. And we can also see that the proposed solution has the best result in relationship with the joint uplink and downlink pilot method used in the literature. This baseline solution assumes that if some users use the same pilot in the uplink direction, they cannot reuse the downlink pilot sequence. Therefore, and also this solution cannot be scalable since it has this restriction. However, we can see that our solution has the best performance and can also be scalable since it is not a joint approach in the uplink and downlink. In these results, we can compare the performance of the AP selection refinement, the proposed AP selection refinement method, and in the normalized mean square error, we can see that the proposed solution has the best performance compared to the canonical self-resistance, and with a scalable system that does not perform the cluster control, and also with the small cell systems in which each user is served by just one access point. For the spectral efficiency performance, we can see that the proposed solution, even though it reduces the numbers of access points that is serving each user, it does not decrease the spectral efficiency of the users, and the numbers of access points serving each user cannot be as small as one, as you can see by the small cell systems, because in that case, the performance of the user is not uniform, and this is not a good approach for self-resistance. We can also see that the energy efficiency of the proposed solution is higher than the canonical self-resistant and scalable self-resist approach. In these tables, we can see the average numbers of access points connected to each users and the numbers of users served by each access point. And we can see that when we perform the cluster control, these numbers are reduced significantly. And when we reduce that numbers, the computational complexity to perform the precoding vectors and combining precoding vectors computation reduces. And also the front hall signaling for the distributed implementation is also reduced since the numbers of users served by each access point reduce. And in these results, we can compare the performance of downlink pilot-based estimation with other approaches. The most common approach used in the literature is the statistical CSI, which relies on the channel hardening and uses just the average value of the effective channel. Another approach is to use the blind estimation, where it is not used downlink pilots, just the downlink received data signal to estimate the channel. And we can see in the normalized mean square error that downlink pilot-based estimation has the best performance than these two approaches. And however, in the spectral efficiency, downlink pilot-based may not be that different from blind estimation when considering maximal ratio precoding, but has a lot of gain compared to the statistical CSI. And if you consider the local partial minimum mean square error precoding, we can see that downlink pilot-based estimation may not improve the spectral efficient performance due to the introduced overhead for downlink pilot-based estimation. And here we can assess more the overhead of the downlink pilot-based estimation, where we vary the numbers of total samples in the coherence interval. We can see that if the numbers of samples in the coherence interval is small, downlink pilot-based estimation may have a high overhead and not improve the spectral efficiency performance. In this case, blind estimation is the best approach. However, when the numbers of samples in the coherence interval is high, downlink pilot-based estimation achieves the best performance. And now we can conclude this presentation. We have proposed a downlink pilot assignment that aims to minimize the pilot contamination and has the advantage of being a scalable solution and can outperform the baseline solution and reduce the normalized mean square error. We also proposed a refinement method for the AP selection, and that method controls the maximum numbers of access points serving each users and can improve the energy efficiency without compromising the spectral efficiency, and can also reduce the computational complexity and the front hall signaling. We compare to other approaches for estimation, for effective channel estimation. Downlink pilot-based estimation can outperform the statistical CSI, the most common method used in the literature, and can increase spectral efficiency by about 80%. And if the overhead is small, downlink pilot estimation is generally the best method. However, in other situations, blind estimation may be the best solution. Therefore, the next step of this work is to design the self-regulated strategy adapted for each scenario to decide when the blind estimation or downlink pilot-based estimation will be the best solution. I would like to finalize this presentation by thanking the supporters and your attention.